Today let us discuss about the Raoult's law. Okay, so this law obeys the what, that is the solution of a liquid in a liquid, right? Okay, now we can say the solution of a liquid in a liquid or a solution of a non-volatile solute in a liquid. So this is the law which obeys the solution of a liquid in a liquid, right? So what this Raoult's law says that, right? So now here, so this Raoult's law, according to this, right? According to this law, what in our solution, you know, we have the solution. So this solution is K containing the two components. So I write a component. We have, okay, one of the components I write a, another component is the B, right? Okay. So now this mixture is what we call the binary mixture. Binary mixture. So in our solutions containing the two components A and B, right? So one of the component is A, another component is the B, right? Okay. So what is the important properties of the liquid? That is the vapor pressure. Vapor pressure, right? Okay. Now here, so in our solution, what is the vapor pressure of the A in the solution? What is the vapor pressure of the B in the solution, right? So the total vapor pressure of the solution is total vapor pressure, right? I write here total vapor pressure of the solution is the vapor pressure of the component A plus vapor pressure of the component B. So we remember these things, right? Okay, so this is the solution. So solution should have the vapor pressure, so that the vapor pressure of the solution is the sum of the vapor pressure of the component A which is present in the solution and vapor pressure of the component B present in the solution. But the question is, so how do we calculate, how do we find out the vapor pressure of the component A in the solution and what is the vapor pressure of the component B in the solution? So this vapor pressure in the solution, we can say the partial pressure of the component A, partial pressure of the component B. Now here, this vapor pressure of the component A, we can calculate it, which is present in our solution, that is according to this law. So what we say, the vapor pressure of the component A in the solution is the product of the mole fraction of the component A and vapor pressure of the component A in the pure state, right? So that is the vapor pressure of the component A in the solution. How do we calculate? So this is the only the simple the equation which can derive from the Raoult's law. That is the vapor pressure of the component A present in the solution is the product of the mole fraction of the component A and the vapor pressure of the component A in the pure state. When we calculate the vapor pressure of the component B in the solution, so according to this law, vapor pressure of the component B is equal to product of the mole fraction of the component B and the vapor pressure of the component B in the pure state. So this is the Raoult's law, what we can remember it. Okay, don't forget. Now, so here, in the previous classes, how do we calculate the vapor pressure, mole fraction of the component A, so and mole fraction of the component B. So one of the very important, so that is the mole fraction of the component A and the mole fraction of the component B. The sum of the mole fraction of the component A and B, so is always unity 1. That means all the sum of the mole fraction of the all the components present in the solution is always the 1, right? So now here, See, the total vapor pressure of the solution. Total vapor pressure of the solution is the sum of the vapor pressure of the component A plus vapor pressure of the component B. So what is the PA? So we can put it here XA is P naught A plus XB P naught B. So this is also Raoult's law, what we can say, right? So this is also Raoult's law, this is also Raoult's law, we can consider, this is also Raoult's law, and this also we can consider. All these are related to the Raoult's law, right? Now here. So by using this equation, what is this equation? That is the vapor pressure of the solution is equal to mole fraction of the component A, vapor pressure of the component A in the pure state, mole fraction of the component B, vapor pressure of the component B in the pure state. So as we know, what is the sum of the mole fraction of the A and B is equal to 1. So let me find out what is the A. I mean mole fraction of the X, because here is mole fraction of the X. So mole fraction of the A is equal to 1 minus XB. So this X value we can put it here. So we can find another equation, that is, let us see, X is equal to 1 minus XB, then multiply by P naught A plus XB, then P naught B. So now here, so we can multiply this P naught A. So we can write P naught A minus P naught XB P naught A plus XB P naught B, right? Okay. Now here, so here the XB is the common, so we can take a common factor. So we can write a P naught A minus P naught A. So I write within the bracket. So when we open the bracket, it should be plus. So that will be the sign minus P naught B. Then I took the common XB. So we have the XB. So this is the another equation we can derive. So here this is the another equation. So this is also one of the Raoult's law, right? Don't forget. So in our competitive examination, right, these types of the equations they can asking you in their options. So this the sign of the what the equations written here. So in the wrong options, it can be plus, it can be minus, it can be minus, it can be plus. By changing this minus and a plus, so it can be given in an option. So our correct Raoult's law is this one, right? And similarly, in other cases, so just I write again this one here. P solution, that is what? Vapor pressure of the solution. So same as I write XA P naught A plus XB P naught B. So now here in the first case, we just find out XA. So now I'm going to find out the XB here, also 1 minus XA, right? So this XB value, let us put it here. What we just find here, that is XA P naught A plus. So now here 1 minus XA, I write in the bracket P naught B. So now here XA P naught A, then now here plus, just bring here P naught B, then it will be minus XA P naught B. Then now here, which one is the common factor here? XA is common factor. So let me bring here P naught B, I just write first, then change the position. Now here XA, then P naught A, now here XA P naught B. So now this XA common factor, I just took it out and now write P naught B plus, now here I write P naught A and then P naught B. So when the brackets, when we open, it should be minus, no doubt. Then when we plus, multiply this sign, is also be minus. So this is the XA. So here is the another equations we can derive it, right? So this is also another equations we can derive. So that is the another Raoult's law. So don't forget. So in our competitive examinations like in the NEET, okay, in the C. So they just put it such types of the options and they can asking you which is the correct option or which is the incorrect option, right? Okay, don't forget. Then now, let's come to the solution. Okay, when we are talking about something, when we are talking about the anything, so it can be as the substance or it can be as the person. So here we just talking about the solution. See, in our solutions we have two different types of the solutions, right? One is the ideal solution, another is the non-ideal solution, right? So question is that what are ideal solution and what are non-ideal solution, right? Okay, see in your class 11 standards we learn about the methods, different set of methods. Here in the gas, so we have the gas also, we have two different gases. One is the ideal gases, another is the non-ideal gas. Or in the case of the solid also we have the ideal solid, solid, another is non-ideal solid, like this, right? So similarly in our solution also we have the ideal solution and the non-ideal solution, right? So how we define the ideal solution and non-ideal solution here? See in our very simple language here. See in our solutions, as you know, solution is the mixture of the two or more components. When we mix two different components, right, there is different phenomena takes place. What the phenomenon? See, as we know in our chemistry, so any substance when we mix together, there is the chemical reaction. So that chemical reaction we can express as chemical interaction. So in our solution, those substances which are mixed together, so there is the interaction between them. So when the interaction between them, so it can be formed another types of the compounds maybe. So in the pure state, the molecule itself, so amongst themselves, in between them, there is some small bonds maybe formed here. That bonds when we mix with another substance, that bond in its case start weaken or start stronger. So that is the phenomenon we can just remember it now here. In our solution, what type of our ideal solution? Here when we mix two substances, there is no any interaction between them. Only the component, only the liquid or only the substance remain there in our mixture. So that type of the solution is very rare. So most of our substance when we mix together, there will be interaction, obviously we should know that. So here or we know that ideality is very rare, but ideality should be there, but it's very rare. That means when we talking about a solution also, when we mix two liquids, there will be the interaction between them. But again, the ideality, it should not be interacted to each other, it should be remain in our solution. That types of the solution we call the ideal solution, but it's very rare. Now here, so when we define the ideal solution, so we have the different conditions, right? So what are the different conditions for the ideal solution? I write the conditions. What are the important conditions for our ideal solution? So as I said before, so I write it here. So this is the intermolecular interaction. So I write intermolecular interaction. Say, let me say our pure component. Let me say pure component. I write in our even in our text also given there in our chemistry. So pure component, let me represent it here, A. So this is the component, so this is the molecules I should say. So this is the pure component of the A, another pure component of the B. So we just write AA and AB. Now another one is that in the solution, in the solution means once we mix these two components, right, these two components in the solution, so this A may be combined with the B, so this is the AB, right? So now here, so this is the components present in the solutions. These are the components in the pure states, right, in the pure state. These are the pure state, right? In the pure state, what are the components? I should say that is the A and the B. But in the solution, when we mix these two components, so what the components present A and B, that is I write AB together, right? Okay. So what is the most important condition for the ideal solution? Here, the intermolecular interaction, of the AB in the solution. The intermolecular interaction of the components in the solution is the same magnitude, similar. Just I write a same, or similar, could say similar with the intermolecular interaction of the component in the pure state. I should say pure state. Let me repeat it once again. What is the most important condition for the ideal solution? One of the most important condition for our ideal solution is the intermolecular interaction of the components in the solution is similar to the intermolecular interaction of the components in the pure state. That is our very important condition. So don't forget, I just said it once again. What is the important condition for the ideal solution is the intermolecular interactions of the components in the solution is similar to the intermolecular interaction of the components in the pure state. Remember. Then, number 2 condition here. Number 2 condition. I write the condition here. What was the first condition? Intermolecular interaction. Number 2 condition is, right? So when we follow the Raoult's law, see Raoult's law. What is the Raoult's law? As I said, the component A, the vapor pressure of the component A in the solution is the product of the vapor pressure of the mole fraction of the component A, vapor pressure of the component A in the pure state. So this is the Raoult's law. Alright, Raoult's law. Then now when we have the solution of the two mixture, when we have the mixture of the two components, that is what we call a solution. Suppose the solution is the ideal solution. That solution, obeys this Raoult's law. Obeys this Raoult's law means the vapor pressure of the component A in the solution, it should be equal to the product of the mole fraction of the component A in the solution and the vapor pressure of the K component in the pure state. It should be equal to, right? Or in the case of the component B, I define it, right? When we do the calculation of the vapor pressure of the component B in the solution, it should be exactly equal to the mole fraction of the component B and vapor pressure of the component B in the pure state for the ideal solution, right? See, when we have the mole fraction of the component A, when we have the vapor pressure of the component A in the pure state, when we do the calculation this, so the vapor pressure of the component A in the solution, it should be equal, right? It should not be different. So that types of the solution, what we call the ideal solution. That means ideal solution obeys the Raoult's law under any condition of the temperature and concentration. Whenever you change the concentration of any or components you took it, when we change the concentration, when we change the temperature, right, that solution obeys this Raoult's law. That means PA should be equal to the mole fraction of the A and the mole vapor pressure of the component in the pure state. Then vapor pressure of the component B in the solution is equal to the product of the mole fraction of the component B and the vapor pressure of the component B in the pure state. That is the second condition, right? Okay. Now I remind you again, okay, what are the important conditions for the ideal solution? Number one, the intermolecular interaction of the components in the solution is similar to the intermolecular interaction of the component in the pure state. Then number two, okay, the solution which are considered as the ideal solution, that solution should be obey the Raoult's law. Okay, under any condition of the temperature, whenever you change the temperature or whenever you change the concentration, that solution should be obey the Raoult's law. What is the Raoult's law? This I show you here, right? Then number three. Now here, see, when we mix the two liquids, right? Okay, obviously the volume should be changing, right? Or when we mix the two liquid, when we have the solution, right, some of the heats are absorbing or some of the heats are evaluated. That means heat changing, right? So this is the our common sense, we know it, right? Obviously when we mix two liquids, so that volume should not be changing or should be changing, or heat can be changed or heat cannot be changed, right? But in the case of the ideal solution, right, when we mix the two liquids in our solution, the volume of the solutions does not change. That means it remain unchanged. What should we express? That is delta V mixing. Delta V mixing means change in the volume of the mixing, okay, should be equal to 0. That means remain constant. Remain constant. That means remain unchanged, right? Then next, what we just find out heat. So I write a heat. So heat in our universal language, that is the enthalpy. So the change in enthalpy, that means heat evolution or heat absorption, right? No heat absorption or no heat evolution when we mix the two liquids, that means is equal to 0. This is for our ideal solution. So we have an important condition here, okay? We have how many conditions I just discussed so far. One is the intermolecular interaction, number 2 is the Raoult's law, and number 3 is the thermodynamic properties. That is the change in the mixing of volume, change in the volume in the mixing, and change in enthalpy mixing. So this much thermodynamic property we can consider in our ideal solution. Don't forget this condition for our ideal solution here. And now here, just I give you very simple the multiple choice, which is asking in your some NIT examinations, right? NIT exam. What the samples I just show you here, I just write, okay? So for an ideal solution, I just write a question for an ideal solution. Ideal solution. This is the question from the past exam and past. The correct option is the correct option. We have to find out the correct option is. So here, number 8. What is the correct option here? That is, so one of the option here, change of the mixing. Now here I write one of the thermodynamic function here, S. What is the S stand for? That is the entropy is 0. What the condition here that is given here at constant temperature and pressure. See, when I explain about the ideal solution, I don't consider this one, right? So this delta S mixing, that means change in entropy mixing, okay, should be 0, right? So this is not our correct option, because I only consider only the two, that is the change in, okay, volume and change of the enthalpy. But for ideal solution, one of the thing is that, see, remember, for ideal solution, whatever, when we mix that our solution, right? So obviously entropy, what it does mean, the entropy, the physical significance of the entropy is the to measure the, okay, randomness or disorderness of the system. What is system? System is our solution, right? Okay. So that means, so when we mix together, solution will form, I mean, when we mix together, the entropy obviously will be increased. That means, okay, the entropy of the solution obviously will be increased. That means randomness will be increasing, right? So that means this is not a correct one, because here the delta mixed entropy is equal to 0, means that it remain unchanged. So that's not for our ideal solution. Second one is, so here is that. See, we are going to find our correct option. So as I explained in the okay, just what is that? This is the change in a volume mixing is equal to 0. Yes, I know that you know it. The answer is this one, right? But what are the others option is given here? So here. So here, so it's written here not equal to. But in this option is given here not equal to 0. If I given here not equal to 0, as I mentioned, the ideal solution, it should be equal to 0. So if I write that this is not equal to 0, so this is not for ideal gas, this is not for ideal gas. So I'm going to write the next option. So that I think it could be very clear to understand. Now I write here delta H. Here is equal to 0. If I write it is equal to 0, that means, okay, this is for ideal gas. So if I write delta mixing, delta H mixing is equal to 0, that should be ideal gas. If we cut it, it's not for ideal gas. So I write that this one is equal to 0. This one is for ideal gas, ideal solution. So one more is given here. That is number D. This is another thermodynamic property, that is the G. Here also given here 0 at constant temperature and volume. So here, so we have the fourth thermodynamic property. One is the entropy, another is the volume. Okay, volume we just related to the ideal solution, but for ideal solution it should not be equal to. That means it should be equal to, right? But here is not equal to. But so this is not for ideal solution. Another thermodynamic property is the enthalpy. Here that should be for ideal solution, that should be is equal to 0. This is the correct option. But another thermodynamic function is the free energy. This is the G. What does G stand for? The Gibbs free energy. Here also the very important thing is that this physical significance of the free energy is to measure the maximum work done, work done by the system, or useful work done by the system. So now here this delta G value is equal to 0. So now here this is also not related to the ideal solution. Our correct option is this one, right? So that's it. Next, now here. Another option I'll just tell you, right? What is the another option here? Yes, before we take the option here. So now here, ideal solution. What type of the liquids mixing are known as ideal solution? Here, so many liquids, many compounds, many chemical substances are there in our chemistry. Okay, so when we mix any one of the liquids, okay, so that mixture can we consider as the ideal solution, or can we consider as the another, the non-ideal solution? So one of the very important chemistry is for ideal solution, what the substance we to get water substance. That means water liquids with to it. Here, that substance, what the chemical similarity is there. So that substance should be having this similar chemical property. Similar chemical properties. So we have some chemical properties. That chemical property, it should be the similar, not the same. So it should be similar. What type of the chemical property we can focus here? See, number one, structure. I just can mention here structure. So structurally, it's look like same. Structurally, it look like same. That type of the two mixture, that types of the two substance when we mixing together, that solution we can consider as the ideal solution. See, for example, here I just take it here. See, now here I write a mixture of the benzene and toluene. You know toluene? See here, what is the molecular formula of the benzene? I just say C6H6. What is the toluene? I think obviously C7. I think H. Okay, how many here? Okay, 5, 6, 7, 8. That means obviously I. So let me confirm the toluene. So we draw the benzene ring here. Okay, we draw the benzene ring here. See, benzene ring, this is also benzene ring. Structurally is quite similar. So only the difference is here in the toluene. One of the hydrogen is replaced by the CH3. See how many carbon here? 1, 2, 3, 4, 5, 6, 7, right? So how many hydrogen is here? One hydrogen is here. One hydrogen is here. 1, 2, 3, 4, 5. Quick. So 5 hydrogen here. 3 more hydrogen here. 8 hydrogen here. So here it's looking very similar. See, carbon is here. Carbon is here. See, carbon here. Hydrogen is also hydrogen here. So when we are drawing this structure, also it's looking very similar. So that type of the mixture we can consider ideal solution. Not only this. Okay. See, I write this one. See, okay. So I just mentioned this pentane. You know, pentane is the hydrocarbon compound. So what is the molecular formula? C5H12. So and another one I took it right here, hexane. So what is the number of hydrogen here? Okay, C6. Okay, so how many hydrogen? 14 hydrogen. See, it's looking very similar. What is similar in the chemical? Chemical similarities here. This is the belongs to alkane. This is belongs to alkane. This also belongs to the alkane. So alkane. I think it's very similar in chemical properties, right? Okay. So these types of the examples we can see very easily. And one is the case similar in structure, or it can say the polarity, right? Polarity. See, polar solvents we can consider here, right? So that types of the mixture we can consider as the ideal solution. So many examples are there in this topic, okay, about the solution. So ideal solution, okay, we are going to discuss about a non-ideal solution. The most important is the examples. So in some of your examination, the mid exam and G examination, so they used to asking them some common question is related to the examples of the ideal or non-ideal solution, right? Okay, now next we go to the non-ideal solution. Non-ideal solution. Here, yes, I forgot to mention here about a non-ideal or about the ideal solution. So when we draw the very simple graph between the vapor pressure and the mole fraction diagram. See here one of the very simple diagram here. See, simple diagram. Now here this is the mole fraction. This is the I write the vapor pressure. If I consider this side is the component A, this side is component A, then this side let me move here component B. Now I just write here is the vapor pressure of the pure component B in the pure state. Now here I just write here is the 1. If I write the mole fraction of the A is the 1, this mole fraction of B is equal to 0. If I said here is the 1, mole fraction of the A is equal to 0. Now here for the ideal solution, so when I draw the one of the curve, it can be drawn like this. This is the one of the graph. Okay, for ideal solution, we always draw the straight line. That means the ideal solution. This one is the B solution. What is that? Is this product, or is the sum of the vapor pressure of the component A, vapor pressure of the component B. Now here, when we just draw like this, it should be straight. When we draw like this, it should be straight. So if I just write it, this is the BA, so that is the XA, P naught B, P naught A. If I draw like this, this is the P naught B, PB, XB, P naught B. So this graph, when we draw it, this is for ideal gas. So you will remember that one. Okay. Now come to our non-ideal solution. See, these types of the graph is shown very clearly in your textbook, so you can go through it. Sometimes it could be very helpful for you. Now we have non-ideal solution here. So most of the solutions which we prepare that are belonging to the non-ideal solution. So 90% of the solutions are related to the non-ideal. Only the very few solutions are we consider as the non-ideal solutions. So because ideality is very rare, okay, but ideality should be there. It's very rare. You keep remember that. Now here, non-ideal solution here. Okay. So what are the important conditions? When we are talking about the ideal solution, also we just start from conditions here, right? So what are the important conditions for the non-ideal solution? Remember, okay? See, I just talking about intermolecular interaction. Intermolecular interaction here. See, in the case of the ideal solution, what's different from the non-ideal solution was the intermolecular interaction of the component in the solution is similar to the intermolecular interactions of the component in the pure state, that was right. But in the case of the non-ideal solution, what's the difference from our ideal solution here? The intermolecular interaction of the components in the solution. I just say AB. A is the one of the component, and B is the another component. So the intermolecular interaction of the component in the solution, so not equal, not same, it's different from the intermolecular interaction of the pure components. Right, I just repeat it again. The intermolecular interaction of the component in the solution is different force, different force, different to the intermolecular interaction of the components in the pure state. That's for the non-ideal solution. Right. Okay. Then number 2, we have the Raoult's law. So if I consider the component A and B, what was the Raoult's law? You know, PA is equal to XA, P naught A. If I just find out the PB, so that is the XB, P naught B. For the ideal solution, as we discussed more elaborately, it was that the vapor pressure of the component A in the solution, it should be equal to the product of the mole fraction of the A and the vapor pressure of the component A in the pure state for ideal solution. Then when we just find out the vapor pressure of the component B in the solution, also exactly equal to the product of the mole fraction of the component B in the solution and the vapor pressure of the component B in the pure state. But in the case of the non-ideal solution, So the solution which we consider as the non-ideal solution do not obey the Raoult's law under any conditions of the temperature or concentration, right? That means the vapor pressure of this component A or component B in the solution is not exactly same with the product of these two. That means not equal to. This is for non-ideal solution, right? So when we write a difference between the ideal solution and non-ideal solution, so we keep remember these things, right? In the very simplest way. Then number 3. Thermodynamically, what we define the non-ideal solution. See, ideal solution, what the important thermodynamic property is, number 1, volume of the mixing. Then number 2, that is the enthalpy of the mixing, right? See, it was that for ideal solution, the volume never changed, it remained unchanged. That means the change in the volume of the mixing is remain constant, that is was 0, right? And the enthalpy changing for the mixing of the two liquids, that also remain constant, that is equal to 0. But in the case of the non-ideal solution, this change in the volume of mixing, this change in the enthalpy of mixing, it should not be equal to 0, right? Either it may be the positive value or it may be negative value. It may be positive value or it may be negative value. Here also this vapor pressure of the component A should not be equal to means it may be greater than or it may be less than, it may be greater than, it may be less than. That means this value may be the positive value, it may be the negative value. So that type of solution, so we are considered as the non-ideal solution, right? Now here, we found here is non-ideal solution. That means interaction, the intermolecular interaction of the component in the solution not the same, that means different to the intermolecular interaction of the component in the pure state. Not the same, different means somewhere else a greater or somewhere else the lesser. That's we just remember. Therefore, non-ideal solutions, we can have two different types of the non-ideal solution. From the above the equation which we wrote it here, somewhere else that is the greater than, somewhere else the lesser than, somewhere else the positive value, somewhere else the negative value. That means the ideal solution, the non-ideal solutions, showing the some positive deviation and showing the negative deviation. It should look like that. Means, see, I just put up here non-ideal solution. We can have one is positive deviation, right? Another is the negative deviation, right? Nothing, very simple difference between the non-ideal solution showing positive deviation and a negative deviation. So when we discussing about a non-ideal solution, just I write the conditions. What are the conditions here? See, remember, intermolecular interaction. Here also intermolecular interaction. Right, okay. So now in our non-ideal solution, the intermolecular interaction of the component in the solution is not the same, that means different with the intermolecular interaction of the component in the pure state. Now here, positive deviation, what the important condition here? The intermolecular interaction of the AB. That means intermolecular interaction of the component in the solution is lesser than intermolecular interaction of the component in the pure states. That means one of the different is what is it? So for the positive deviation, the intermolecular interaction of the component in the solution is lesser than the intermolecular interaction of the component in the pure state. Don't forget. But in the case of the negative deviation, this intermolecular interaction of the key component in the solution is greater than intermolecular interaction of the pure component. That is, we just write here, right? That is the difference. Okay. What it means that, see here, in our liquids, okay. So suppose I just take ethanol. How we write ethanol? That is, I write C2H5, so bond should be here like this. So in between the oxygen and hydrogen, so slightly polarity is developing. Now here it's developed positive charge, here it will be positive negative charge. In the ethanols, I write ethanol C2H5. Now here this is the oxygen and the hydrogen. Here it sends the negative charge, and since this carry positive charge in between these molecules, right? So this hydrogen and this oxygen can be interacted with each other and form the bond. This type of bond, what we call the hydrogen bond. This is the strong bond, I should say, in the ethyl alcohol. So here in ethyl alcohol, right? So I add the one of the so liquid, that let me say acetone, right? I added here acetone. In the ethyl alcohol, when we mix with the acetone, so this bond it's weakened here, right? It's make it bracket this bond and form the starting form bond between the ethyl alcohol and acetone, right? So that types of the mixtures, what we should call the positive deviation, right? Now here in the positive deviation, see the escaping tendency of the vapors, right? It's very high, I should say. If the escaping tendency is very high as a vapor, that means it can be that, okay? So if the vapor pressure is the very high, if the vapor pressure of the solutions are very high, right, the boiling point of this solution will be the very low, right? That means that types of the mixture should boil at the low boiling point. That means at a low temperature, right? Okay. Then now here, so this is the one of the condition. Then number two condition, as we know here, this is the first condition, this is the second condition. What is second condition here? In our non-ideal solution, as I write here, P A not equal to K X A P not A. If I write a P B not equal to X B P not B, not equal to means K greater than or less than, right? The positive deviation, this equation, just we can write the PA should be greater than XA P not A. Then PB, I just consider here greater than XA XB P not B. Right? But in the case of the negative deviation, it should be the less than. It should be less than. Right? It should be less than. Here in our negative deviation here, okay, so the intermolecular interaction of the component in the solution is the stronger, is the greater than the intermolecular interaction of the components present. See, for example, I should say that here in our negative deviation, say, let me say here, okay, say acetone, this is the acetone, right? So here in our acetone, right? See, in our acetone, the acetone molecule does not have any chance to form the hydrogen bond. No chance to form the hydrogen bond. But yes, interaction is to be clear. So what type of interaction? It can be dipole-dipole interaction. So that types of interaction it can be mentioned here. So that interaction is very weak here. So now when we add the one of the liquids that can be say the chloroform, right? Chloroform. So when we make this chloroform, this oxygen and one of the hydrogens present here, it can be formed the hydrogen bonding. That means the intermolecular interaction between these two, it's very higher than the intermolecular force between this component itself, right? That types of the measure we call the non-ideal solution showing the negative deviation, right? Then here number 3. Yes, I think it's very easy to understand. What the number 3? What the number 3 is? See, as we know thermodynamically, what we should write is here delta is mixing not equal to 0. That means for positive deviation, it should be what should be the value? It should be positive value. That means greater than 0, right? That means what will be the value? What it does mean? This change in enthalpy, the value comes up positive means here is the heat absorption. Heat absorption, right? So when we are talking about the change in the volume, here also it should be positive values. That means the volume of the mixture should be increased. That means increase the value, increase the volume, right? If the volume increase, if the heat absorb, when we have the mixture of the two liquid, that type of the solution we call the non-ideal solution, showing the positive deviation. But in the case of the negative deviation, what is it? So this delta is mixing, that means enthalpy changing, it should be the negative. That means if the enthalpy change is given out of negative, that is the evolution of the heat. That means heat evoluted, right? Okay, that means it's less than 0. Less than 0 means Z, negative value, right? And the volume of the mixing, that also less than 0 means that will be the negative value. It means the volume will be decreased. If the volume decrease, or if the evolution of the heat takes place, right? If the value of this is less than product of these two, that type of the solution, that type of the non-ideal solution is negative deviation, right? Now, as I said before, regarding the solutions, the examples of the liquid mixtures are very important, right? So now here I just take the one example. This I take it one question here. See, I already here. This is the question from your NEET examination. What the question is? The mixture with soap. Which shows positive deviation. Positive deviation from the Raoult's law. From Raoult's law means ideal solution. Positive deviation from Raoult's law. Here is the ideal solution. We are talking about it. So this is the ideal solution, right? So when we are talking about the ideal solution, so that solutions, so it's from the non-ideal solution. That non-ideal solution where some values are positive value, some are negative value. That means the positive value shows that the positive deviation, the negative value shows that that is the negative deviation. So that are related from the ideal solution as well as the non-ideal solution. Now here I just give you the 4 options. What are the options here? Number 1. Number 1 is ethanol plus acetone, right? Number 2 option is benzene plus toluene. Number 3 option is acetone plus chloroform. Number 4 is chloroethane plus what is it, bromoethane. Right, okay. So now here let we think about the ideal solution. Here is some of the options are given here related to the ideal solution. Look at, see, as I before mentioned that for ideal solution, right? So chemical similarity should be there. What the chemical similarity? So it may be in terms of the structure or in terms of the polarity or in terms of some chemical properties, right? Now here benzene and toluene have some similarity. So these types of the mixtures that are related to the ideal solution, right? Number 2, that is chloroethane, another is the bromoethane, right? Here chloroethane, see, you know chloroethane, what is the formula? We can write Cl, another is the C2H5, that is the Br. See, chlorine and bromine, that is the same family that belongs to the halogens. So that means there are some similarity. And another is the ethane, right? So ethane is same, no doubt, right? So this chlorine and bromine are also same family. There will be some similarity in chemical properties. So this mixture that also belongs to the ideal solution. So this cohesion, that means showing positive deviation. So this is not our correct option, this is also our correct option. Now here we have a 2 options here, ethanol, acetone and acetone and chloroform here, as I said before, right? See, ethanol, when we mix acetone, see, in the ethanol there will be the small hydrogen bonds there, right? So that hydrogen bond is weakened or it's breaking down when we mix acetone. That means interaction between these components is lesser than the interaction between our pure component. See, the acetone, as I said before, see, acetones no chance to form the hydrogen bond in the pure stage, right? But when we mix with the chloroform, so there will be the chances to form the hydrogen bond between the acetone and the chloroform. That means intermolecular interaction between our components in our solution will be greater than the intermolecular force between the pure components. So that means this is for negative deviation, this is for positive deviation, right? So our correct option is ethanol and acetone, right? So remember this one. This is question from our the past mid examination, right? And now here, see, we draw the graph as we drawn here, right? So this is the component A side, this is the component B side, right? Just I put it here, this is the vapor pressure of the component A in the pure state, this is the vapor pressure of the component B in the pure state. Now this side, the mole fraction of the component A is now taken as 1, mole fraction of the component B is taken here as 1. Now the mole fraction of the component B should be taken as 0, the mole fraction of the component A should be 0, right? And now this is the graph, that means this is the diagram, that means vapor pressure and mole fraction diagram we can see. Now here, this is the px diagram. P means the vapor pressure, x is the mole fraction, right? So this is the vapor pressure and mole fraction diagram. Now when we draw the graph for ideal solutions, obviously the graph should be straight line, right? Then when we connect these two, it should be always a straight line, no doubt. This is for ideal solution. But for the non-ideal solution, this graph should not be straight line, right? But what should be the graph? So we have the 2 different non-ideal solutions. One is the positive deviation, another is negative deviation. How should draw our positive deviation? Nothing, simple. When we draw like this is the positive curve, right? When we draw like this is the positive curve like that, right? This is for positive deviation. if we draw this just downward, everything downward from the ideal solution that are related to the negative deviation. That's all simple, right? Now here, finally, let's just think about our solution. Just we have the another properties, that is the boiling point, right? See, boiling point is another properties of our liquid, remember, right? See, as you will know, vapor pressure is related to the vapor pressure is related to the boiling point also, right? What is the relation between the vapor pressure of the liquid and the boiling point of the liquid, right? So remember that vapor pressure, if the vapor pressure is the high, that means higher the vapor pressure of the liquid, right? What about the boiling point? The boiling point should be lower, right? That means those liquids having the high vapor pressure, they boil at low temperature. Understand? Then those liquids having the low vapor pressure, low, right? So that vapor pressure, that boiling point should be very high. Okay? So now here, some of the liquid having the high vapor pressure, that liquid should be boiled at a low temperature. It's simple like the ethanol. Ethanol compared to the water, has high vapor pressure. Obviously, boiling point should be very low. Okay, understand? But in our waters, the vapor pressure is higher than the ethanol, lower than our vapor pressure is lower than our ethanol. Definitely, the boiling point of the water is higher than our ethanol, right? So, keep remember that one. What is the relation between the vapor pressure and the boiling point, right? That means higher the vapor pressure, lower the boiling point, right? Lower the vapor pressure, higher the boiling point, right? And now, in our mixture, the two liquids when we mix together, it forms the solution. Remember, different liquids have a different vapor pressure. Understand? And different liquids have a different boiling point, right? Once we mix together some of the mixture, right? So if the vapor pressure is large different, if the vapor pressure is large different, the boiling point also be large different, right? Okay, obviously it may be higher or it may be lower. That is the condition for our vapor pressure of the particular liquids given. But the thing is that, so in some cases, in some solutions what we mix together, right, if the vapor pressure is very closer to each other, right, so boiling point also it should be very close, remember, right? If the vapor pressure of the two different liquids, two large different, right, so there can be different boiling point, right? But only the thing is that when the two liquids having the very close vapor pressure should also be close in boiling point. So therefore, some of the solutions, so the mixture of the two liquids, that is the mixture of the two liquids, right? That types of the two liquids boil not a different boiling point. Boil at one temperature. So though the vapor pressure different, boiling point also definitely should be different, but the liquid mixture, those liquid mixtures boil at one temperature. That types of the mixture we call azeotropic mixture. What do you mean by azeotropic mixture? So, what do you mean by azeotropic mixture? Mixture of the two liquids, right? Boil at 1 temperature. That mixture what we call azeotropic mixture. Clear, right? So in our azeotropic mixture, right, so the boiling point of the azeotropic mixture, okay, some of the azeotropic mixture boil above their boiling points, right, and some of the azeotropic mixtures boil below their boiling points. So here we have two different boiling points of the our azeotropic mixture. One is minimum boiling azeotrope. Number two is maximum boiling azeotrope, right? Okay, so what are the minimum boiling azeotrope and what are maximum boiling azeotrope? Means, as I said before, okay, mixture of the two liquid boil at a particular boil at a 1 temperature, but that mixtures boil above their boiling point or below their boiling point. The mixtures boil, okay, above their boiling point, that is the maximum boiling azeotrope. The mixtures, okay, of the two liquids boil, okay, below their boiling point, that is the minimum, okay, boiling azeotrope, right? So now here, what are the mixtures and what mixtures shows the maximum, shows the minimum boiling azeotrope? Now here, very simple is that minimum boiling azeotrope means those liquid mixtures, right, so their vapor pressure of the solution, is higher than vapor pressure of the pure components, right? I repeated that. What type of the solution, what type of the mixture of the liquids, right, shows the minimum boiling azeotrope, that is, okay, the vapor pressure of the solution is higher than the vapor pressure of the pure components present, right? That type of the mixtures, it shows the minimum boiling azeotrope. So that type of the solution is, okay, non-ideal solution is showing the positive deviation, right? So what are the examples are given in the non-ideal solution showing the positive deviation? That mixtures are related to the minimum boiling azeotrope, right? See, as we saw our positive deviation with what I given here, ethanol and acetone, okay, ethanol and acetone. So that is the example of the positive deviation. That mixture shows the minimum boiling azeotrope, right? Then what is the maximum boiling azeotrope, right? Now here, what type of the mixture showing the maximum boiling azeotrope means, okay, the vapor pressure of the solution is lesser than the vapor pressure of the pure component, right? That types of the mixture we just call, we just says that, okay, negative deviation, right? Negative deviation. So that types of the non-ideal solution showing the negative deviation, that it shows the maximum, okay, boiling azeotrope. See, I just give you the example one, very simple. Water plus highest NO3, nitric acid. So this mixture, these two mixture, so it shows the negative deviation and it shows the maximum boiling azeotrope. So here, the most important I repeated here. So examples of the different types of the solution. For ideal solution, what are the mixtures of the two liquids, and for non-ideal solution, what are the mixtures of the liquids, and in the positive deviation, what are they, and negative deviation, what are they. At the same time, just we should remember that solution minimum boiling azeotrope and maximum boiling azeotrope. So these are the important things regarding our ideal solution and non-ideal solution, right? Okay, see you then.